I will be talking about work that I did during my PhD because I only started a month ago. So the work that I will be talking about is actually joint work with my PhD supervisors, Meylahn and Arnold de Boer from the KDVI here at the University of Amsterdam, as well as some work I did with my brother who in the University of Twente. Yeah, please interrupt me at any point. And I've clicked. So that's not working.
Is that the Zoom and not the slide? Maybe you're clicking on the Zoom.
So I should be. Okay. Thank you very much. All right. Okay, here we go. It's working. So I will first introduce the basic framework that can be applied to all the models that I study, and also motivate a little bit why we want to do these things. And then I will talk about 3 projects. The first is on interpersonal trust. The second continues this line of work, but transfers it a little bit into an all or nothing public goods situation, which is also a model for trust, I claim. And then finally, I will end discussing a model on opinion polarization. So the motivation for why we might want to do this, okay, so social dynamics have been studied extensively, right? Especially by the means of models. Why would we do that? Models allow us to make precise what we mean, what our assumptions are, and then we draw the conclusions based on these assumptions, right? So we interrogate our assumptions and we check that, is it really true what we think we believe as the premise? And once we've confirmed that, we study the model and then we draw conclusions and say, well, if this is how it is, this can emerge, this can happen as a result of that. Of course, a lot of models can be, some people might say, too simplistic, which, you know, does allow for extensive analytical study, which a lot of us are big fans of. But they can also be too complicated, right? So we can have a very simple, I see this behavior and I'll copy it, and that can be read than that. And then we can also go to the other extreme and have, you know, age and economic things and take everything into account. And then, well, it's difficult to say, well, what really caused the behavior that we're seeing. And so in this talk, or the projects that I did, we're trying to look for a middle ground. So we're trying to look for somewhat tractable models with a touch of realism. And the touch of realism that we will use or proclaim is agent learning, right? So having each person that we model use some kind of learning rule from their experience. So we say that we're not just mimicking, we're not just copying, but we learn from what we've experienced in the past. And we'll find that the models don't become too intractable. Okay. So the overarching framework that can be applied to all of these models has agents in some environment. Each agent has a belief which influences their actions. And these, so you can use there this idea of rationality, taking the action that optimizes my expected utility. And then the environment will respond with a signal. And the signal is then taken as an experience to the agent, which they use to update their belief, right? And the border between agent and environment is a little bit loose because one agent could be the environment for the other agent. In fact, for all the models, that is the case. But I didn't want to have all of that in one picture. So we will model trust and opinion dynamics with learning. And because this signal from the environment can be the experience for the other agent, we can also talk about that as if it's social influence, some form of social influence. And then where possible, we will also include a network structure and say, well, what does it matter how these interactions are located in some kind of a network? And does that make a difference? All right. Jumping straight into the first project, first model. Why do some of us trust our neighbors? So what we see here from the very nice and handy website, Our World in Data, we see the share of people agreeing with the statement, most people can be trusted. And we see that that is not evenly distributed across the world, right? We see, very trusting places like the Scandinavian countries, as well as China. And we see much less trust in South America, as well as South Africa, where I'm from. And so we want to see, well, what kind of elements may play a role in determining what kind of a situation results, right? So what might be the determinants of high or low trust in our neighbors? But of course, we will use a very basic model. So per round, we will draw 2 agents from a population of n agents, and they will be matched, right? So we'll just label them 1 and -1. That is for convenience. They will have their own indices if you want to think about the dynamics of the system. But in this round, they will get a new label, just so we can refer to them nicely. They will observe their own payoffs in a payoff matrix pi k at time t. This payoff matrix is drawn IID in each round. So there is some distribution of these payoffs, and that gets repeatedly, and you only see your own payoffs, which therefore allows a little bit of the reasoning that you'll maybe see later for why you might behave in this way. Because if you knew your opponent's payoff, of course you can use other rules from game, results from game theory to determine what your behavior will be. But because you only observe your own payoffs, we believe this behavior makes a little bit of sense. You choose an action based on these payoffs, as well as your estimation of how trustworthy the population is. So that's x, k at time t. So this x models the belief. And that is how likely they believe that some random other person will be trustworthy or play the trustworthy strategy, right?
But is that a given you put in?
Sorry?
You put in that function?
Which function?
How trustworthy the population?
It's a belief. It changes. So that will update. That will be influenced by the learning rule. So that is something that will change over time. And how that'll change will become clear in a moment. So based on this interaction, both agents will update their belief according to simple exponential smoothing, which is how this X is updated. And I'll go again into more detail. I think maybe this exposition of this model could be optimized, but I kind of like doing it like this. So we have a relative overview, and we'll get into the nitty-gritty in just a moment. Okay, so this pi at time t has the following form. So we've got 2 actions, trusting and doubting. And the trusting action results in this payoff lambda. These lambdas are specific to the agent, so those don't necessarily need to be the same, but they are drawn IID, but the agents don't know this. They don't need to know this. If I trust and the other person defects, I get 0. And if I defect, I will get 1 always. So that is the safe option. The riskless, the risk-free option is just to defect or doubt, and then I will just get the payoff of 1. Well, let's talk about this lambda some more. We'll say it's got support on 1 to infinity or less than infinity, but over there in the positive numbers, bigger than 1. And that is true for both agents and for all time t, right? And these get drawn IID. So now we've merged 2 things. We've said trust action is the same as trusting as well as being trustworthy, because you could, in a trust game, you would have 2 different roles, and you would have someone that places trust and someone that honors or abuses that trust. And in this case, we've just sort of smushed those together to make the study possible. But we think it's a relatively acceptable assumption for now. We'll get there.
Okay.
We'll get there.
This is just a prisoner's dilemma, right?
It's a little bit similar to the prisoner's dilemma. It's a coordination game. The prisoner's dilemma is not a coordination game.
So defect is 1-1.
Yeah, so defect is actually going to always be worse than trust because lambda is always bigger than 1 or equal to 1. Right? So trust is always bigger than or equal to defect. So it's not a prisoner's dilemma. It's a coordination game. So doubting, and then doubting is not trusting as well as abusing someone else's trust. We will get to the lambda, trust me, but for now I will go first to the agent actions. So we write the probability that agent K holding belief xk at time t will trust as the probability that this lambda times their belief is bigger than or equal to 1, right? That's just a utility maximization, one round utility maximization. Do we agree? I think so. I don't see too much consternation.
So I'm very concerned about the word myopically.
Because they don't consider what happens in future rounds. So it's just one round expected utility. So that's myopic.
Okay.
So I just care about my very next payoff. Yeah.
And then, so X is the belief that the other person is going to
Play trust. Yes.
And it's equal for all.
No, it's per agent.
But it's per agent, but everyone else is regarded equally.
Yes, because they interact with everyone. So it's very similar to that first question. Most people can be trusted, right?
Yeah.
So in this case, there's no network, and it's just a random person. My belief that a random other person in the population will be trusting, right? Because you could say, okay, it's if you're just looking at one other person, you would have information about that person. But in this case, you can also think about saying, oh, the population consists of so many trustworthy people and so many not trustworthy people, and this proportion is equal to the chance that I interact with someone who can be trusted.
Yeah.
Right? Similar things, different interpretations. Okay, so we've got this probability that I place the trust action given that my belief is X. But we can rearrange this. So we define a new random variable Z, which is 1 over lambda. And this will have CDF, cumulative distribution function F, such that the probability of placing trust is equal to the CDF at X, right? We do this for convenience. So we don't actually really think about the distribution of lambda. We think more about this distribution of 1 over lambda. And from our assumption on lambda, we've got at 0, the probability of trusting is 0. At 1, the probability of trusting is 1. And in between is in between. Yeah? Yeah? Okay. How do agents update their belief? So simple exponential smoothing or exponential moving average. Same thing, different name. With a constant learning parameter alpha, takes the following form. If my opponent plays the doubt action, I shrink my belief a little bit by multiplying my old belief by 1 minus alpha. And if my opponent plays trust, I increase my belief a little bit. Yeah. So it's a very simple learning rule that has seen some success in other regions. And we thought, well, it's nice and relatively easy to study. So we'll use it here. So with all that information, knowing how agents take their actions, how their beliefs will change as a result of those actions, we can draw the expected motion, right? And it's especially easy to visualize for 2 agents. So we've got the 2 beliefs on the X and the Y axis. And we say, given that the beliefs are here, and knowing the distribution of 1 over lambda, which we just set, so that's here, either this or that, we can write down what is the expected next belief for both of these agents.
Okay, I have a feeling I have asked all these questions before.
Yes.
But in the f of x, you just give it. You try different things and.
Yeah. So the point is that our theoretical result will hold for almost all f with some minor assumptions. So that's the nice thing about it. But yeah, you can plug almost anything in there. So we'll see. Maybe we'll expect vastly different behavior for different f's, right? So this one, it looks like everything sort of gets pushed towards the center, and things should stay there. And here in this one, it looks like everything gets pushed to the top right corner. And well, if you were to take sort of the expected dynamics, this is what you would find. But the actual dynamics look quite different. So, okay, again, a new f of x. This one is just f of x is equal to x. So you'd assume that any point where my belief is equal to my opponent's belief is some kind of stationary point. But because you do take one action and you don't take half of an action or whatever, we find that the dynamics bump around in the middle for a bit and then get absorbed in one of the corners. And this can be either of the corners. That we formalize in this theorem.
I'm sorry, but that was for the linear one. What happens in the other ones that you just showed?
Also the same thing.
It goes to corners.
Yes.
But is that because the corners are observing state?
Yes.
But the other one didn't.
The stochastic person always reaches an observing state.
Yeah, but it took quite a bit of work to show that it was an absorbing state. It also took quite convincing of my supervisors that this is actually what happens and that they don't absorb in the middle. So it seems very logical in retrospect, but we were surprised, and I had to fight a little bit tooth and nail to convince my supervisors.
But the plot you made of the function before, yeah. So here the corners are. How do I see the corners are absorbing space?
Exactly, you don't, but they are. That's why the result is surprising. So that's the. I mean, look, yeah. So this also very much depends on the fact that alpha is constant. So if you were to have a decreasing alpha, so a learning rate that shrinks over time. So there's arguments for and against this. Arguments for this is you think, okay, there exists a true answer and I'm going to look for that. Then you would shrink your alpha. But if you say the population can also change, so I want to be adaptive, right? So if you use exponential moving average and you're just trying to track something else that isn't related to this, having a constant alpha allows you to change when that thing is changing as well. And so that, giving the agents that kind of generosity to say, well, look, they're going to be flexible, actually makes them inflexible, right? Because of that, they necessarily get absorbed in one of the two columns. Yes?
Maybe it doesn't matter how to interpret these pictures, but I mean, I think if I, on average, have to follow these arrows, I mean, I just, on average, should enter wherever the arrows point, or...
Yes, but you don't, on average, follow the arrows.
That's
because you always...
For the arrows. You just...
That's the expected. It's the expected motion, but it's because the actual motion is always going to be either in this direction or in that direction, and never actually in a combination of the two. Yeah.
So these arrows don't really have a meaning.
They are the expected motion. You say, okay, I have this belief, I have this distribution of f, and then I say, well, what is the probability of being there and the probability of being there? I sum that up, and then I get a vector, and that's my arrow. How does that not have a meaning?
No, but in the sense that if I'm doing let's say symmetric random walk, I mean, my average step size is 0, but every step I do go left or right.
Exactly.
And so
it's very related to this.
Okay.
Yeah. You have a random walk on this 2D plane, and then you happen to hit the corners in your stuck.
Basically. Now it's a lot less exciting. Thank you. Thank you kindly. No, that's very fair. Okay. So that was with a fully connected population. There's some minor conditions on F that actually turns out can be relaxed for a lot of cases, but we don't need to get into them right now. So the next thing is we move on to a network interaction. Okay, so now instead of having a fully connected population and just drawing 2 agents at random, I extend it to an interaction with more than 2 agents per round, right? A network that is not fully connected, but any connected network. And we will discuss more detail about the random geometric network.
Sorry, more than 2 agents per round.
In playing the game.
Okay, so your matrix will change. Is it three body interaction?
Yes, yes, yeah. So n, some number n that can be
okay.
2 but can be bigger. Yeah. And the underlying rule here, or the idea, is that all agents need to play the trust action in order to get the public good. Otherwise, it's not awarded. So you can think of that as some kind of natural resource, maybe, and as soon as one company pollutes it, it's ruined for everyone. Or you can just think of some kind of veto power that everyone has. Everyone has some kind of veto, and as soon as one person says no, then no one gets the benefit of the public good. How realistic that is can be debated, but we thought it's a reasonable starting point as well. And how do we select? So how do we know how many agents are in the interaction? So here's an illustration. Suppose this is our network. Then we will draw one agent at random. In this case, that's agent 6. That's why they're circled. And then agent 6 and all of their neighbors will play a round of this game. Yeah. And this also a little bit makes sense why there's no like reputation or things like this, because agent 5 doesn't actually know agent 7 and 8 personally. There's no link between them, but they do have to play against them sometimes. And so it's sort of a little bit justifying that they would behave in this way. Of course, you can make it more complicated if you like. Long story short, in a connected graph, the same result is still true. So we do a Borel-Cantelli argument. We define the corners. So epsilon ball around 0, epsilon ball around 1. And then we have to prove that absorption in the corners is possible. It's a little bit of work, but we get there. And then we show that reaching the corners is possible from anywhere that is not the corner. And then Bob's your uncle, you have absorption guaranteed, right? From the previous story, this is not surprising, but it took a little bit of more work now because we have network interaction. We've got multiple, we don't know how many people will be in the interaction per round, all of these things, but it works out. But now we can also study the effect of the network, right? So what happens if you change your network topology? How does that influence where you end up? So in this interaction, because it's all or nothing, if I have belief X, the probability of taking the trustworthy action is now X to the power of the number of players minus 1, right? Because I need everyone else. So it's the probability that I will get this reward of the public good is the probability, well, I will choose what I do, and everyone else's action is modeled by my belief. And so I need all of them to trust. So if I want to make some other threshold rule, then I can just change this exponent. Probably it won't change too much. And that influences how the size of the interaction changes the dynamics. And we'll see, or we do see, that more connections leads to more defection, so more doubt. Well, let me first say what's on the pictures, and then I'll say why we see what we see. So on the left, we have circulants. That's a regular graph. You just put all your agents on a circle, and you connect for these blue triangles, my right and left neighbors. For the orange circle, sorry, for the blue triangle, yeah, for the orange circle, I will connect also to the next one, so 4 nearest neighbors, and so on. That's the circulant. And then the random geometric graph, I just pepper my agents onto the plane, onto the square, and then I will draw a radius around each agent of different sizes. And if the other agents fall within that radius, I will connect to them, right? But we restrict ourselves to connected random geometric graphs, just so that we don't have to study what's happening in different components. Okay, what do we see? Well, in this lowest connection circulant case, actually all the simulation runs ended in complete trust. So all agents trusting. In the higher two, so L is 6 and 8, L is the number of nearest neighbors, all the simulation runs ended in all defect. And in this orange case, so for 4 nearest neighbors, it was more or less an even split. And this makes sense if you look at this CDF, is because now each agent is always, the interaction is always the same size. And well, within an interaction of 5 people, so myself and 4 nearest neighbors, the probability of trusting is now f of x is equal to x, right? And so that doesn't have a clear bias one direction or the other. Whereas if I have more agents, then I have a function that sort of points towards the bottom left corner. And if I have less agents, I have a function that points to the top right corner. Okay, so we see more connectivity leads to less trust. And the same is true in the random geometric graphs. So we have here basically the same story, but for the smallest radius, most of the runs led to consensus, and for the biggest radii, most of the runs led to all doubt. And this explains also why it's not a monotonic relationship, right? So as we increase the number of nearest neighbors, we go from here to a slower dynamic and then to a much faster dynamic, and that is related to how biased the situation is. If I have a system that is clearly more biased to a doubt steady state, then that will happen quickly. If I have something that is clearly biased towards a trusting steady state, as in this case, that happens quickly. And then for this edge case, it's more of a random walk that is more unbiased. But we also see qualitatively different behavior. So we've got here a log-log scale. So this is the survival probability. I didn't know, maybe I should have explained what that is. So that's the probability at time t that my absorption happens after time t. Yeah. So the dynamics take also a qualitatively different shape in the random geometric graphs, and this is related to the heterogeneity. So now I can have regions of low connectivity and regions of high connectivity, and these play off against each other, where it looks like they will reach some kind of steady state with mixed situations. But by our theorem and also in the simulation, we see eventually one eats the other. But the time that this takes is much longer. What is
this like? Can I think about this as in a sort of other way where, because I mean, the longer time it takes, it reminds very much of this critical slowing down of the phase transition. So can I think about this as sort of, you have the connectivity is some sort of control parameter, and the order parameter is the high or low trust consensus, and then you increase the connectivity, you go through a phase transition from high trust to low trust.
I would imagine so. I don't see why not.
Like that.
I didn't take that approach, but I would imagine that makes sense. It sounds plausible. So what this looks like on the network itself, we have here runs that didn't converge in our simulated time. So we didn't want to overload this poor machine and set a limited number of time steps. And well, we see that this heterogeneity is observable, right? So we see here the bluer the node, the less trust they have, the redder the node, the more trust they have. And we see regions of high connectivity has low trust, and regions of low connectivity has high trust. And this is a little bit nice because it mirrors a little bit also what we see big city life versus out in the countryside, right? Where in the city, no one greets each other and you lock your bicycle twice and all these things. And out in the countryside, if you pop in to get some bread at the baker, maybe you don't even lock your bike. And this, it makes sense because it's just the number of people that you don't know how they will interact that might come across. I don't know. It's a story. And what this looks like so over time. So if we plot here the total belief of the agents over time, we see that it looks like some sort of quasi-stability. So you reach some state where these agents are all having low trust and these agents are having high trust. And it looks like this will continue for quite long. And then eventually it just jumps to one of the corners and then there you are and you stay there. That's quite possibly not surprising now that you know the rest of the story. But we were studying this and we found these results, and we thought it looked quite similar to a different model on opinion polarization. which used Q-learning. So there were some subtle differences there between our model and this model. But we thought, well, it's weird that they present their model with different results. So what is that model? So 2019-ish, Banish and Olbricht illustrated how social reinforcement can lead to persistent opinion polarization. It was nice. It's a very nice paper, especially it was a new concept at the time. So having this reinforcement learning in opinion dynamics had not really been done. And it was also quite an astounding result because they reported stable polarization in a model with no repulsive forces. So in this Q-learning model, if you interact on the dyadic level, always you will become a little bit more similar in terms of which opinion you think is better. And still, they said, well, in this model, polarization can be stable. But they did study it only with simulation, and so we thought, well, let's see what if we apply our techniques to this. So I phoned my brother and said, hey, let's do a project. You've been doing some things on Q-learning. I've been doing some things on social dynamics. Let's get together, and we did it. So what happens in this model more precisely? Again, we'll draw a random agent from the vertex set uniformly at random. This agent now expresses an opinion, a binary opinion, to one of their random neighbors in that graph. And so the opinion expressing is -1 or 1. So that's always like a discrete action like we saw previously. But how they do this is slightly different. So here we have a schematic. On the left, we sort of show what the initial agent that is selected does. And on the right, we show what the responding agent does. So the agent that observes this expressing of opinions. Right. So all agents have a pair of Q values now. Instead of a belief on one parameter, they've got a pair of parameters. One of these is bigger than the other, and that gives them a preferred opinion. And then with probability 1 minus epsilon, they will exploit that preferred opinion. So they will express the opinion that they believe has a greater Q value. And with probability epsilon, they will explore by expressing the other opinion, right? This expressed opinion gets sent to the neighbor that they have selected to share their views with, who has their own Q values. And so if the observed opinion matches their own preferred opinion, they will send a reward. So we'll send Rj is equal to 1. And if the observed opinion does not match their preferred opinion, they will punish. So they will send this Rj is equal to -1. The initial agent then takes that and updates the Q value only for the opinion that they expressed. So some differences between this model and the previous models is that, well, there's a pair of Q values here that are uncoupled. So the agent doesn't take into consideration that there are only two opinions and that they could, in theory, infer that if they expressed the other opinion, they would have gotten the other result and then updated actually both Q values at the same time. It's asymmetric, so that's why we'll refer to this as the ARLOD model, the asymmetric reinforcement learning opinion dynamics model. So only the initial agent has the chance to explore, and only the expressing agent updates their views, right? And that is something we will take into question later.
Can you remind me the alpha parameter? Goes into the
that is the learning rate. Again, so very, very similar. Also, this update is very similar. Just sometimes we will subtract alpha where previously we just did the little shrinking that happens here. Right. So that's another similarity. Right. So I will jump again to the.
Sorry, maybe how you said it, but the 1 minus alpha comes for what exactly?
So this 1 minus alpha is shrinking the Q value a little bit, and then either adding alpha to increase it because I got a reward, or subtracting alpha to decreasing it even more.
Yeah, that part I understand, but the 1 minus, so if alpha is large.
So alpha is also between 0 and 1.
Sure, but okay. If it's
and it changes how much my opinion changes. My Q value changes based on my feedback. So if I have a big alpha, my Q values will jump a lot. And if I have a small alpha, then my Q values will only change a little bit.
Equals to 1 means what?
Alpha equals to 1 doesn't happen, but that would just be that I make my value 1 if I get a reward, or 0 -1 if I get a punishment, right? Because then my old belief doesn't matter anymore, and I change my belief. Then it's a voter model, basically.
No, but alpha equals 1 means I don't learn anything, or it means I learn.
No, it means you adjust very much. So you might be overcompensating. Right? So you get your reward, and then you'll increase your Q value for that opinion a lot, or you'll get a punishment and you'll decrease it a lot. So it just changes your sensitivity.
Yes, sorry. Sorry. The last term is okay with me. The thing that you just explained. The middle term, that's the thing that
That's the same alpha.
Yeah, so alpha, I know it's the same alpha, but if alpha equals 1 there, you don't get that term. And I'm just asking why you don't get that update there.
I mean, you will update just to 1 or -1.
Yeah, I guess you update on the response, but you don't update on that part. And I'm just asking. Just take RJ equals 0. RJ equals 0.
RJ equals 0 also doesn't happen. RJ is always 1 or -1. But sorry, I mean, if RJ is 0, then you have no Q value. Then there's nothing changing. Then nothing happens.
If alpha
Everyone's
1.
Yes. Then
Yeah, I'm asking what does that mean?
that doesn't mean anything. That doesn't happen. It's not part of the model. RJ is always 1, and alpha is always between 0 and 1. Maybe we can discuss later. So I can.
Q bound? No. Can it be anything?
Q is it'll be between 1 and -1.
So maybe I can add something. Hello?
Your neighbor, if alpha 0, you
Yes,
basically don't care. You
Yes.
have your own opinion, and you don't care what anybody says.
Okay.
Yeah, sorry, I tried to say that, but maybe I didn't do a good job.
Hello?
Someone is saying something online. Please speak.
Yeah, so the 1 minus alpha for the Q value is because you're taking a convex combination of your old Q value with your new information. And if you didn't have the 1 minus alpha, your Q values would diverge.
Okay. Yes, I know.
Thank you, Jonas.
The same way of speaking. Yeah.
All right. Okay, so it might not surprise you again because, well, it's the same talk and we've seen it now happening a couple of times, but we'll find that consensus is guaranteed asymptotically, so polarization is not stable. And we also find that under a very specific form of batch learning, this model resembles a voter model, and symmetrizing this interaction makes it ergodic. So we'll dive into more of those later, but that is the overview of our results. Right, so you've seen the shape of this before. If at some point all of our Q values have the same ordering, then that stays forever the case. And that is related to the constant exploration rate and the constant learning rate, and also related to the asymmetry. So same strategy again. We show consensus is absorbing, and that is because of the asymmetry. So because my responding agent never explores, as soon as we all agree on which opinion has a greater value, if I express that one, I will get bolstered, and that value will increase even more. And if I'm exploring, then that one will lose Q value because I will get punished, because we all agree. So once the ordering of agent Q values is universal, this gets reinforced and is completely stable. And then we show that you can reach consensus from any non-consensus state. So that can ripple even from one agent to the rest, all having the other ordering. That is possible. But of course, the converse is more likely. And this is because everything is finite. So the number of interactions you need to do that is finite because the alpha is constant and the epsilon is constant. And so this finite sequence of actions required to switch has a positive probability. And then, well, the same result holds. Yes?
Maybe this is a more semantic question, but I think if you talk about consensus, so if everybody distrusts everybody, then you call this consensus.
It's not a model about trust anymore. This is opinion dynamics now. So this is now the two opinions. They don't need to be trust and not trust. But and we would call that consensus. In the other models, we would still also call that consensus because everyone agrees that everyone is not trustworthy.
Yeah.
That's still a consensus.
Okay. Yeah.
Yeah. Okay, and in practice, we observe some similar behavior. Also, the shape looks very similar, and this in this case is related to clustering. So if you have because there's no high connectivity, low connectivity changes in the dynamics towards one opinion or the other, so towards trusting or not trusting. In this case, it just matters that you've got separate clusters that can converge on different opinions. That looks quite stable for a long time, but isn't in the long run. And so we see with network heterogeneity, we see these long times to absorption. Now, if we do these very special batches, so suppose we have an agent that the agent gets selected, and then they will just interact with agent J until their preference matches, then you have a voter model. And because basically any sequence of events in this actual model, so before this batching, happens at sort of a lower probability than in this batched version. We have that anything that is sort of stable in the voter model should be, or metastable or quasi-stable, should be as stable in our model. And so so this, I mean, I think most of you are familiar with the voter model, but basically, we select a random agent, and then they will select one of their neighbors, and they will switch their opinion to that opinion. So with probability 1/3, this agent 1 keeps their opinion because one of their 3 neighbors has the same opinion, and with probability 2/3, they will switch. And we show that these two have the same distribution if we're talking about the same graph. And this sort of tells us that anything that is, as I said, anything that is sort of somewhat stable in the voter model will be also stable in this model, or have a similar stability, being quasi, so not asymptotically. And so we see that again happening here. We've got a jump to something that looks very stable, where this portion of the network has opinion 1, and this portion of the network has opinion -1. And we think, oh, that can continue forever because it stays the same or same-ish for about some millions of time steps, but eventually we jump out and we can observe that behavior as well. But now the assumption of this asymmetry is something we thought was quite peculiar, because it's something to assume that both agents wouldn't learn from their interaction, right? You get together, you have a cup of tea, and both of you will chat about things. And well, unless one person is very dominating, probably if you have different opinions, you might feel comfortable to say that in that situation. And maybe you go home and both of you reflect on what the interaction was like. So now we will change everything to lowercase to say that we're in this different model. And the only thing that changes basically is that both agents can explore and exploit. So both agents will express an opinion, and then they will update their belief. And instead of this R, which is just 1, they will get 1 or -1. You just multiply the two opinions by each other. So either we agree, -1, -1. So then I will increase my Q value, or we disagree, and so we will subtract alpha. And then I will weaken my Q value for that opinion. And in this case, we show that now the situation becomes ergodic. So you can get a consensus state where everyone has the exact same ordering of the Q values, and you can actually just jump out of that because the exploration is constant and the learning rate is constant, and we can also observe this by simulation. So not only is it true what we say, well, we know it's true, but we can also observe this behavior and see the switching from consensus on one opinion to the other. So what do we learn? Why is this true? Well, again, it's a finite sequence of interactions that is required to make that switch, and we can bound the probability of those actions by epsilon squared, the lower of the two, so the probability of exploring. And because it's finite, it's bigger than zero, and very similar to what you've seen now a couple of times. We get this reachability.
Because it's ergodic, you also mean you can end up everywhere.
Yeah.
Yeah. Okay.
Yeah. So this, what did we learn, or what did I learn during this process? Timescales are important. So we study social phenomena, and a lot of people, I think, from certain aspects are quite interested in certain results being also true asymptotically. And the question is, do we need that to be the case? Because we don't even know if the dynamics we see in the real world are stable, right? So we could be, focusing less on that and saying, well, let's think about what happens at intermediate timescales and also discuss the dynamics there, and not be focused on, well, if my model ends up in consensus eventually, then it's boring. We also learned that reinforcement learning has potential for modeling in the social dynamics of trust and opinions. So we saw now some models where that happened, and these models are not impossible to study analytically. So we prove some theoretical results, and these guide our simulations and how we frame the results of those simulations, right? So if we didn't know that convergence was guaranteed, we talk about the probability of converging, right? The probability of consensus, instead of saying the probability of consensus by time t, because we know eventually it happens. And this framing might be relevant. And seemingly innocuous assumptions on the dynamics may be more important than grand assumptions about the network. So that's lots of big words, but in that Banish and Ulbrich paper, a lot of effort was put into discussing the effect of the network. But this asymmetric, the decision to make the interaction asymmetric was, I think, glossed over a little bit maybe. And this assumption is quite important for the dynamics. I mean, ergodic dynamics versus non-ergodic dynamics with absorbing states is quite a big difference. And so I think this is just a lesson in, digging deeply about our assumptions and making sure that what we say is important is really as important. I don't mean that the network is less important, just that some other things might be similarly important. And some references. Thank you very much. Questions? Yes.
For the first part of the talk, cumulative distribution function f of x that you mentioned. Is there any link to sort of real world data and what that might look like for population?
So it was not something we thought about digging into. If I had to think about that now, I mean, similar. I guess there's literature about these kinds of interactions where everyone has their own valuation of how good some result is, and I think that literature would be a starting point of where I would tug to find out if there's data about this as well. I think more common is that they actually just draw a single value per agent. So an agent will just have one lambda for the whole game, where we draw it independently per round. So, but it shouldn't change too much. Yeah.
If I can ask a second question, just because I think I might have missed that part of the talk. In the second part, you mentioned reciprocity versus non-reciprocity leads to different behavior.
You mean symmetry?
So sorry, yeah, of the interaction.
Yeah.
Symmetry versus
Yeah.
Was this to do with ergodicity? So one of them leads to ergodic behavior.
Yes.
And which one was it?
The symmetric one.
Leads to ergodicity.
Yeah. Which makes sense.
Okay.
Right. I mean, then more things can change.
Yeah.
If there are no more questions, then we should thank the speaker.